Hello and welcome. In today's video, we're going to be covering how to conduct a one-sample t-test using the statistical software Jamovi. So if you haven't downloaded Jamovi, you can do so for free, and I can link that in the description. And I'm also going to have a dataset linked in the description below, so you can follow along throughout this tutorial and click all the same things that I'm clicking on. So by the end of this video, what I want for you is to understand what a one-sample t-test is and the kind of research question you could use for a one-sample t-test. I want you to know the assumptions of a one-sample t-test and how to check those in Jamovi, and of course, how to conduct a one-sample t-test analysis and interpret the output all within Jamovi. So download that dataset in the description and let's get into it. To begin, what is a one-sample t-test? A one-sample t-test is an analysis that allows us to compare two means. One of those means will come from a sample of data, and we will be comparing that sample mean to a mean from a broader population. So for example, if you're a teacher and you want to compare the ACT scores of the students just in your sample classroom with maybe the national average, the means in your classroom would be that sample mean, and then some broader population average, the average national ACT score for that year would be your population mean. And you'd compare those, and you determine not only are they similar or are they different, but specifically if they are statistically significantly different from one another. So for our example today in this data set, let's say that we've got a couple who has been budgeting and they've been keeping track of their weekly grocery budget. So we have their weekly grocery budget average, and that's going to be our sample mean. And what we're going to do is we're going to compare that couple's weekly grocery budget average. We're going to compare that with the average weekly grocery budget for couples nationally. So when we open up our data set in Jamovi, we're going to go through how we can test the assumptions of that kind of analysis and then how to actually conduct the analysis and take a look at the output. So what you're going to do when you get into Jamovi is you're going to go to Analysis, then you're going to select T-Test, and you'll see that there's going to be three options there. And the one that I want you to select for this is going to be the one sample T-Test. Once you do that, you're going to see a couple of options for different variables. Our variable for this is going to be the grocery budget per week, right? Those couples have been budgeting, they've been keeping track of their budget for the week, and we've got that sample there. So you're going to move that over to our dependent variable. What I want you to take note of is you're going to see a little ruler icon next to that variable name and in the dependent variable box. And that's because one of the requirements for a one sample t-test is that the dependent variable be measured continuously. And that's what that little ruler icon notes. So if for some reason when you are working in Jamovi, if your variable does not have that ruler icon next to it, you're going to want to make sure that you go in and click on that variable and change that so that it's labeled as measured continuously. So we've got all of ours in order here. The next thing that we need to do is if you scroll down to hypotheses, you're going to see an option for test value. In that box, we want to type in 175 because that's going to be our national average grocery budget for couples. Now, whenever we are working with the one sample t-test, remember, we've given our sample data to Jamovi and our data set, so Jamovi knows our sample data, but we're comparing our sample data with that average population mean as well. Jamovi doesn't know what that average population mean is, so we have to tell Jamovi what it is. So in this instance, we're going to say that the average grocery budget per week for couples in the US is going to be $175. You also will see that Jamovi has it automatically selected for the not equal sign there. What that means is that we are going to leave it open for Jamovi to detect statistical significance at both ends of the tails of a normal curve. So if the value is statistically significantly greater or statistically significantly less than our sample value, that's fine. We're open to statistical significance on either end. The next thing that I want you to do is under additional statistics, I want you to select for the mean difference and the confidence interval, and then also for the effect size and the confidence interval, and for descriptive statistics. We'll go through these one by one here in a bit, but all of these provide additional important information about what's happening with our analysis. And then importantly, you're also going to check under assumption checks for the normality test and the QQ plot. And that's where we're going to begin. So assumptions are a series of standards that go along with statistical analyses. And we need to make sure that we have met those assumptions prior to completely interpreting the results, so that we can make sure that our interpretations are accurate. So there are two important assumptions of a one sample t-test that I want to talk about with you. The first one is the assumption of independence. This assumption states that each of the data points are independent from one another. One data point isn't influencing the other data points, and this is really important. However, this is an assumption that we usually take care of prior to data analysis. So we would try and make sure that we have independent data points as we are collecting data and designing our study. But once we get into Jamovi, we don't typically look at this assumption within Jamovi for the one sample t-test. However, the other assumption that I want to talk about is the assumption of normality, and that assumption we do assess within Jamovi. The assumption of normality states that our dependent variable is normally distributed in the population, and we can assess that in two different ways within Jamovi. So one of the ways, if you selected the normality test, you'll see we have something called the Shapiro-Wilk test. This is a test that tests our sample distribution and compares it to a perfectly normal distribution. Now, normally when we see a p-value that is below 0.05, we might get excited and think, oh, that's a good thing because we've determined that there is statistical significance. However, when we are looking at our assumptions and we see a p-value that is less than 0.05, that still indicates statistical significance, except this time we don't get excited because that statistical significance means that our sample data was statistically significantly different from an ideal normal distribution. And that's no good because we want our data to be normally distributed. So the Shapiro-Wilk test gives us a p-value, and here our p-value is around 0.95, which is far above that 0.05 threshold. So we can say, yay, we have met the assumption of normality. Our data are normally distributed. Now on my screen, you're going to see a couple other tests here as well. And that's because one of the great things about Jamovi is that there are many different modules that you can download to allow the software to do even more things for you. I downloaded a package called More Tests that gives me more tests that I can take a look at in Jamovi. That's not required for this particular analysis, but if you'd like to download more modules, I definitely encourage you to do that. But either way, whether you've downloaded the more tests or not, you should see the results of the Shapiro-Wilk test there. So another way that we can make sure that our data are normally distributed is through a QQ plot. And unlike the Shapiro-Wilk test that gives us a p-value, the QQ plot gives us a visual way to examine the normality of the data. And what we're looking for here is that the little dots that you see there are tightly aligned with the line there on the plot. If we see a lot of variations with the dots from that line, then that tells us, we might want to take a deeper look because our data might not be normally distributed. Another important thing that I want to keep you aware of is that violations of normality in t-tests don't always have to mean that we can't move forward with the analysis. There's a saying that t-tests are robust to violations of normality. And what that means is that if we violated normality and our data are not perfectly normal, we might still be able to move forward with the analysis if we have a sufficient sample size. The rule of thumb, according to the central limit theorem, is that if our sample size is at least 30, that should approximate normal. So you can keep that in mind. If you ever have big concerns about normality, you can look into something called non-parametric testing, which we won't cover in this video, but I'm happy to answer questions about if you have them. So we've talked about independence, we've talked about normality, we've met that assumption of normality based on the Shapiro-Wilk test and the QQ plot. So now finally we can take a look at the output of the one sample t-test analysis. So I'll have you scroll back up and you'll see there's a one sample t-test table. There's lots of information in this and I'll go over it with you. So first we have the test statistic. This is the value of t. So our value here is negative 66.1. This value in and of itself doesn't make as much sense on the surface until you look at the associated p-values and degrees of freedom and things like that. So this value of 66.1, is that value statistically significant, right? That's what we want to know, is if our sample mean is statistically significantly different from that average population mean. So that's where we can take a look at this p-value here. And the typical threshold for determining if a p-value is statistically significant is if it is less than 0.05. So our p-value here is less than 0.001. So we can determine that these two means are statistically significantly different from one another. Another piece of data here that's important is something called the degrees of freedom. This can help us also understand our sample size. So in one sample t-test, the degrees of freedom are going to be equal to n, or our sample size, minus 1. So if we have a degrees of freedom of 149, that means that our sample size was 150. Now, we know from the p-value that the two means are statistically significantly different from one another. But you might also be wondering, okay, so the weekly grocery budget of the couples on average is statistically significantly different from the national average, but how different are they? And that's where that mean difference can come in and help you understand even more. So that mean difference says that the two means are $76.2 different. So one of the means was around 100 and the other mean was around 175, because we see that we have that 76-ish point difference in the two means. Now, if we wanted to give ourselves a little bit of room to say, hey, this mean difference, this is an estimate because we just have a sample. So we know that there could be bias there. We think it's around 76, but it's even more likely to be somewhere between 78.5 and 74. And that's what that confidence interval does for us. It gives us a spread to go along with what our estimate is there. And then lastly, what I asked you to select as well was something called the effect size. So the effect size gives us information about the magnitude of the effect. The p-value tells us, is there an effect or not? The effect size tells us how large that effect might be. Cohen's d's effect size, which is what we use for one sample t-test, are a standardized mean difference effect size, which means that it is in standard deviation units. So this means that there is around 5.39 standard deviation units between the sample mean and the population mean. That's quite a bit of standard deviation units. And I can help you understand that even more by letting you know that the rule of thumb is that an effect size is considered large at values of around 0.8 for Cohen's d. So this is 5.39. So well above that 0.8 threshold to be considered a large effect size. And just like for the mean difference, we know that this is a sample, and so there could be bias associated with this value. And so we also provide a confidence interval. So we say, we think the effect size is around negative 5.4, but it's even more likely to be somewhere between negative 6 and negative 4.75. So you might be thinking, okay, well, all these values are negative. What does that mean? How do I interpret those values? So I will say, don't panic if you see values that have a negative in front of them. That just means that the value for the sample was smaller than the value that we put in for the average. So if you scroll down to your descriptive statistics, it'll give you the information about the average dollars spent per week for the sample. That's that mean value right there. So we can see that on the couple in our sample, they were spending around $98, $99 per week, whereas the national average was that $175. So our sample value was smaller than our test value or our national average value, and that means that some of those values like t and the mean difference and the Cohen's d are going to have that negative sign in front of them. But that's nothing at all to worry about. It's just how the algebra works out there. So while you're looking at the descriptive statistics, you also have information, of course, about the sample size. You've got the mean, the standard deviation. This all helps us get even more information about what's going on with our data. So we've covered the assumptions and how to determine if they've been met. We've covered how to conduct the one sample t-test analysis and how to interpret the output. If you have any questions at all, please feel free to leave them below, or you can reach out to me through my website at ajoytoteach.com, and I'm happy to help you more there too. Thanks so much. Bye.